Okay, everyone, welcome to the, let's see, what month is this? November Robothon exhibition event. So as many of you know, we were not able to do the live events either this year or last year. So we're doing these exhibition events and various other contests in place of that. So what we have today is just a series of short presentations. They'll be about 15 to 20 minutes apiece. We have 5 presenters. Dave Mier, you're first on the list, talking about Autodave. And we're just going to kind of go through the list as they appear on the website. At the about 1 hour mark, we'll probably have gone through the first 3 people. We'll take about a 20-minute break, and then we'll come back and pick up the last 2. So that should get us wrapped up about 2 o'clock-ish, or maybe 2:30, depending on overlap. After that, folks are welcome to hang around. I'll try to remember this to say this again at the end. But after the main event, I'll turn off the camera. Folks are welcome to stay in the room and hang out and chat. So any questions, thoughts, comments? I'd like to welcome everyone, by the way. One more thing, I know we've got people here from Vancouver, Canada, I think. And I know we've got people here from the Dallas Robotics Group, so welcome. Do we have folks from anywhere else? Let me ask that real quick.
There's a couple from the Southern California Robotics Society of Southern California.
Oh, cool, awesome, welcome.
I'm from Ottawa.
In Ottawa, wow, okay, awesome. We got people from all over the place. That's the nice thing about doing these online presentations this way. And by the way, just one more quick note before I hand off to Dave. We do intend to keep doing these, even when we go back to having in-person events. So we'll try to, there's just things you can do here that you can't do in person and vice versa. So with that, I'm going to go ahead and...
Lloyd, can I just interject for a second?
Yeah, go for it.
So what we do in general for our online monthly club meetings, as well as these special events, what we do is we record them and then we place them out on our club's YouTube channel. So for reference material, refresher, etc., you're always encouraged to go back and review content such as this. So back to you, Lloyd.
Okay, thanks, Donna. And at that point, I'm going to hand it off to Dave Mier, who is going to do a presentation on Autodave, which is his SRS Magellan robot. And oh, Randy, did you want to say something? Nope. Okay, I saw you were physically raising a hand. Okay, off to Dave, who's going to talk about his SRS Robo-Magellan and PopCam Challenge robot. All yours,
Hi.
Dave.
Yeah, thanks, Lloyd. So I'm Dave, and I'm here to talk about my robot, Autodave, right behind me here. So this is my Seattle Robotics Robo-Magellan and PopCam Challenge robot that I put together. So normally right around this time, we're competing. We're just wrapping up our competition. But today, since we're meeting virtually, I'm just gonna talk to you about my robot and share how I built it, kind of what that story is. And really, I want to encourage participation, either from like just coming to watch or even building your own. So it's a really fun experience for me. So let me share my screen here with you guys. Hopefully it's coming through for you. So yeah, let's get into it. So yeah, I'm here. I live in the Seattle area. I've been doing personal, like, hobby robotics for about 15 years, and time flies. When I started doing robotics, I didn't know anything. I didn't know how to solder, or I didn't know microelectronics or anything. So building this robot's given me an opportunity to kind of learn and explore all this with a central purpose. So the photos you see up here. So this, if you're not familiar, this is what Robo-Magellan looks like. So you're outside. So it's a very challenging environment, rain or wind, leaves on the ground. And the challenge is you start at one cone, and then maybe about 100 meters away or so, outside of visual range, you can't see it. There's a destination cone that the robot is tasked with navigating autonomously to. So all I get to do as the engineer is I get to hit start, and then the robot is on its own to find the destination cone. So usually it's down at the Seattle Center. You can see the Space Needle here. So usually we gather a decent sized crowd. So it's a lot of fun. So that's Robo-Magellan. This is my robot here. So the left photos, that's kind of how my robot looks in its operational configuration. So it self-drives. It's basically a laptop on an RC car. And I put that skateboard in there because it actually played an important role in helping me develop my robot. I'll show you later how. And then underneath the laptop, so if you take the laptop off the top, you look at the electronics underneath, that's what that right photo is. So there's quite a bit going on, a lot of wires, but it wasn't always that complicated. So I started building things one component at a time. So, and over, keep in mind, it's been 10, 15 years or so. So it's been quite the project. Just in general, at a high level, what I've done is, so I started with a commercial off-the-shelf RC car. And I took an Arduino microcontroller, and instead of connecting the RC car steering and motor controller into the radio, I plug it into the Arduino. And then the Arduino plugs into a laptop. And that's the basic description of how my robot works. Here's a video from my first Robo-Magellan. This was in 2009, I think. You can see me chasing after it. I actually have a string tied to the robot, so if it gets out of control, I can actually restrain it from going where I don't want it to. But it was very, very challenging. I had no idea what I was doing, and the robot was quite unruly there. But you know, that's what it was. It's just an RC car with an Arduino and a laptop, and that's all you need to get started. So after reflecting on my first Robo-Magellan, now I think, well, it might be good if the robot actually had some kind of sensing capabilities. And so so now I have my standard configuration up top, and I was like, all right, here's a bunch of sensors I have. So there's things like inertial measurement units, Hall effect sensors to serve as wheel encoders, GPS, LiDAR cameras. There's a whole range of sensors that you can learn and integrate into the robot. And that's what I've done. And it's helped me. So the first sensor that I put on my robot was it's an inertial measurement unit. So it uses accelerometers, gyroscopes to determine what direction the robot is pointing. And so you can see here, it's already doing a little bit better than from 2009, that first Robo-Magellan. But if you can see the robot, it's doing kind of a drunken swerve where it's going left and right. I had no idea what I was doing at the time. It turns out that I had discovered a need for control theory. So you can actually solve this with a PID controller. So let's see. I got a question. Let's see if I can field that real quick. The link from Arduino PC is just USB for programming. Yeah. So there's, at this point, there's really no radio frequency communications. I use it for safety, so I can stop the robot, and I'll show you how that works. But the link from the Arduino to the computer, it's sending the sensor data. So the inertial measurement unit is sending data to the Arduino. The Arduino collects that, sends it to the computer, and then that's how I process the steering command to send to the robot. So, yeah, so I've Velcroed a laptop to the top of the robot. That's how I solved that. So here's a little bit more of the video of the robot. So I figured out how to stop it from doing that drunken wobble, and now it's driving consistently in straight lines. And when I got to this point, I'm like, wow, this is something that I don't think I could even drive it this precise, you know, if I was remote controlling it myself. I mean, these lines are pretty straight, and the turns are, I mean, they're with robotic precision. I think they're pretty cool. So so at this point, I'm like, wow, I want something. So I kept doing what I was doing. So here's my design. So this is probably the most technical slide. But the point I wanted to show you, at least to interest new builders or folks who are considering building their own robot, is when I first started, all I had was a laptop and an Arduino. And then my first project was figuring out, how do I connect the Arduino to a laptop? Then I got that. That was one weekend. And then the next weekend I figured, how do I connect a servo into the Arduino? And then I was like, okay, well then how do I control a servo for my laptop? So each one of these lines that you see here, it's about a weekend project or two that you work on. And then before you know it, after years and years of trying things out, you have this, you have something, and it's pretty cool. So for example, so I think I saw a question about how the laptop works with Arduino. There's, can you have the Arduino do the yeah, you can. So let's see here. The reason I kind of got into this is I was exploring, you know, all the various technical aspects of robotics, teaching myself as I went. So what I am doing is, so the inertial measurement unit, it's sending basically the pitch and the roll and the yaw of the car in real time to the Arduino. The Arduino collects that, and then it sends the data to the laptop, where I have lots of compute power. I mean, I can do many things, and I'm more comfortable in high level programming languages. That's my background, is computer science. So I do kind of all my high level logic in the laptop, and then I send basic commands back to the Arduino, which it's better at controlling, reading sensors and controlling servos. So then the Arduino will issue the proper steering command. So my PID controller, for example, if you wanted to implement that on the Arduino, you could, but it's going to take a bunch of your compute cycles. So I just offload that to a laptop. But yeah, so these are all the sensors that I've worked with over the time. If you have questions on anything specific, we can talk more about specific implementation. So let me tell you a little bit about that skateboard, because this is where it played a pivotal role. So one of the first things that I realized that I wanted to implement was some kind of safety remote. So in 2009, I was chasing after it with literally a string tied to the robot so it didn't escape. And when I wanted to stop, it would kick up dirt. You know, it's still going full throttle and dirt gets all over you. It wasn't a lot of fun. I was like, there's a better way. So on the left here, you see it's a packet radio. So I think it uses 433 megahertz. I think it's the free radio spectrum. And so you put one module on a handheld remote, and I just wired up some buttons there to tell it, you know, what I wanted to send. And then there's another remote on the car. And then that way I could integrate with the Arduino, and the car would stop safely, and I wouldn't have to get dirt all over me when I tried to pull on the string. And this was great. It worked very well, but the way I practice my robot is I go to the park right next to my house. I skateboard there, and I had my robot in one hand. I had an orange practice cone in the other, and I'm going down on my skateboard, hit a small bump, and I fall right on my back. I'm not very good at skateboarding. I'm better at robotics, but I land right on my safety remote, and I crack it in half. And I'm like, oh, geez, I finished my day before I even started. So, you know, at first I was a little sad, but this kicked off another challenge for me. Is I need to make a safety remote for my robot that can not only control the robot, but can withstand a skateboard crash. So, you know, this kicked off a whole nother project of mine to design a better safety remote that's a little more professional looking or put together in a solid product. So, you know, I honed my soldering skills, learned a little bit of CAD and 3D printing. So I from the from the maker perspective, I mean, this pulls everything together. So you can see as I'm constructing this here on the bottom left, like it's starting to look a little bit more like a finished product here. And then that's what I have here on the right. So I've actually made two of them. One was made with a proto board. And then I even built another one where I made my own printed circuit board in EagleCAD. And, you know, so looking back at this, I'm just like, wow, having that skateboard crash, where I cracked my remote open, it really gave me an opportunity to build and learn how all this can be put together into a product. So, anyways, that's my skateboard story. So eventually you get a robot, you know, after practicing, put together, and it's functioning pretty well. So here's down at the skate park. So this is the robot. You know, I figured out how to drive in a straight line now. I figured out how to turn. And then there's even some other challenges on here, like just even going up a hill. So how do you go up a hill at a reasonable speed? That's something that takes challenge. You also use a PID controller as well. But yeah, so I just has the robot. I program a single course, and I just tell it, you know, do it 3 times, and you know, then it goes off on its own. I think it would do it all day. It's very repeatable, and so it's yeah. So this is kind of where it stands right now as far as what it's capable of doing. So I wanted to touch a little bit on the software aspect, and I think I saw a question we can check in there. So all of this is done in a 10. But I do a detection cycle. It's a observe, orient, decide, and act cycle, and I do that 10 times a second. And so all of my sensors are collecting data. They can collect it much faster, but I just decided, you know, the fastest that my hardware is capable of doing is all of this processing and computing once every 10th of a second. So that's how I process it. So let me check out one of the questions. Could it be that the delay to send the laptop back to the is contributing to the oversteering results in swerving? Yeah, so there's a lot of things that affect how the robot is doing. Delay is one of them. How am I doing localization in that? So I do have some localization. Primarily, what I found was most effective is I just do dead reckoning, and so I use a wheel encoder, which is really, it's just a magnet. I have 5 magnets taped into the side of the wheel. I have a Hall effect sensor taped to the axle, and that's how I do my encoding. It's very crude, but it works. And so I get my distance. The inertial measurement unit gives me the heading, and so with that information, I can do some localization. I also have GPS. I don't use it. I haven't. I found the dead reckoning is more accurate. The GPS sensor I have only updates once every second. So I see a question on error compensation. You know, I just don't do it. And that's been a challenge. So the further the robot goes, the more error that collects into my estimations. So yeah, so that there's ways to improve that. Right now, I'm actually looking into Kalman filtering to help me eliminate some of that error estimation by normalizing with the GPS sensor and diffusion. It's complicated, and there's a lot to learn for me, at least. So, but that's what I'm looking at. Okay, let me go on to the next slide. So here are my outtakes. It hasn't always been perfectly driving. So that top right video, I figured out how to drive in a straight line, but I didn't figure out what direction straight line, so it crashes into that parking garage thing there. The top left was me working on turning, so it turned a little too fast there. It's an RC car, but it's much heavier, and so it rolled over on top. Dell is a good manufacturer. They have a great warranty. But yeah, I do beat up my laptops. I'm on my 3rd laptop now. And then this bottom video, the robot I think it had a full battery, and it was ready to go. It gets up on 2 wheels here. So that's some of the fun stuff that you get to do. But I will note, nothing. I've never really damaged any property or hurt myself or anyone with the robot, so I'm happy. I have driven into a concrete wall though twice. But anyways, so that's kind of my story with Autodave the robot. Here's just some shop pictures around the shop. As I'm building this thing together, you can see some of the mechanical components. This is why I went with an RC car, just because there's enough complexity in building a robot. I figure, I can eliminate some of that by just buying an RC car. But yeah, the wiring gets pretty intense for a while. But yeah, overall, it's been a lot of fun. And this all started with just a RC car and an Arduino. And I would say you don't even need a laptop. You can do a lot of that on the Arduino, but the laptop makes it easier to access for me. So yeah, I'm looking forward to next year. So hopefully we'll be out at the Seattle Center and we'll be competing in person. And we're always looking for enthused roboticists to come out and just making that first step to see what you can do with just an RC car and an Arduino. You'll have a fun adventure. At least it's been for me. So I'll wrap that up and back to you, Lloyd. Thanks.
Dave, this is Donna. Can I ask you one other tech question?
Yeah.
Regarding your laptop configuration, are you running a version of Linux, and if so, which one, or Windows OS?
So my laptop has both. So it has Windows, and I'm actually using my laptop that goes on the robot for Zoom. But it's running Windows. When I'm commanding the robot, it's in Linux. I think I use Debian just because it's easy.
Okay.
And then yeah, the software on the laptop's all written in C++, but really you can use anything. It just sends and receives serial data through the USB cable to the Arduino.
Great. Thanks.
Yeah.
Great job, Dave. Thank you so much.
Yeah, thanks.
Is there time for another question?
Yeah, go for it. We got time for a quick question.
Okay.
So I'm just blown away that your dead reckoning is as accurate as it is. Are you are you correcting for drift with like a compass or using GPS or accelerometers, or is any of that other sensor data being used to correct it, or is that just seriously dead reckoning?
Yeah, that's dead reckoning. And it's not very good dead reckoning either. I mean, so my one rotation of my wheel has 6 ticks of counting. So yeah, I was surprised how repeatable it was too. It gets a little off when you're in like wet grass because the wheels will slip a little bit more. But when you're on like pavement, there's not much wheel slippage. And then the only real error that you get is any drift that you would get from your inertial measurement unit.
I'm wondering if that's if you're getting really good dead reckoning because your RC car chassis is really high quality, because usually the steering mechanisms on those have a little bit of wobble in them and there's a little error, but apparently the one that you're using is really tight and accurate.
Yeah, it's worked out. It's not perfect. I mean, I would say, if I drive like that course in the skate park, it might get off by like 6 inches or so from when it was last time. And that will build up over time. So the longer you go, the more error you get. But yeah, I've been surprised about how accurate and repeatable it's been with just dead reckoning.
I had a question. I put into the chat about how you hacked the car itself.
Let's see. Well, maybe so we can talk about that. I don't want to go too far over our agenda.
Yeah.
Maybe let's talk about that in the chat afterwards. I think we can address that. But yeah, it's definitely possible. I'm happy to talk about that too. So.
Sure.
Okay, thanks, Dave.
Mm-hmm.
So moving on. Let's see. What did we start? Okay. moving on to the next person, James Newton with SDMG bot. Pretty sure I saw you come in, James. Yep, there you are.
Yeah, I'm here. I thought Donna was going next, but that's fine. Whatever order you want to go in is. I just finished eating my sandwich, so I'm good to go.
Those extra questions, Dave, paid off.
There you go. So let's see. I guess what I want to do here, if possible, is share the screen.
Yep,
I'm not sure. I'm not sure whether or not.
Or James, excuse me.
Now, are you seeing the Robothon here in the upper left-hand corner? I can't see what's being shared. Yeah, that looks right.
Yep, that looks right.
Okay, so just a quick little introduction. My name is James Newton. Good grief, I thought I combed my hair. Apparently not. And I've been told that I need to spend a little bit more time talking about what my bona fides are or my past experiences. So I'm always uncomfortable doing that, but I'm going to push myself to just do a quick introduction. So bear with me. I figure I'd practice on you guys because you'll be nice. My current day job is working for Haddington Dynamics, which is a division of Ocado. And we build this Dexter robot arm, which is, believe it or not, not this version, but the prior version of it is in fact open source. And I would encourage people to take a look at this web page that I will paste in the chat really quick here, because there is a lot to learn from this system. It is very, very well documented and is very complicated, and there's a lot of cool stuff in it. My involvement personally in robotics started when I was a kid. My father and I built a robot with a RCA 1802 microcontroller with the Nedtronics Cosmic Elf, and we resist ink etched a motor driver board and some relays and got some motors and stuff. So that was my introduction to that. Then I really got into 3D printing, and I came across a stepper motor driver that wasn't commonly available, which I made available to people through an open source, which I made available through an open source driver, and hooked it up to some standard Merlin ramps controllers, and a guy named Andre over in Wisconsin decided that that was exactly perfect for the house cement printer that he wanted to build. And so you can see my drivers in his control box and the castle being printed in the background, and that's the castle that he ended up printing. His company went on to do a lot of 3D printing of houses outside the United States. And then that was in 2015, and in 2016, a young college graduate by the name of Alex LaRue came along with this company he called Vistaprint at the time, and they wanted to make a 3D printer just like Andre's, so they bought another set of, you can see the drivers in there. And that company ended up being acquired by Icon, and so you may have seen their 3D printers. Now they are, of course, both of these guys have moved on to using, very big and expensive servo drivers, which I didn't start learning about until a little bit after that. So this is a servo driver that I've made a couple of years past that. That's a treadmill motor, which is it's just a little bit under 2 horsepower treadmill motor. And there's the position sensor right here, DC motor driver, which you can drive these motors DC. They're standard brush DC motors. And they're available for basically next to nothing if you get them out of old dead treadmills. Usually it's the electronic controller that goes dead and the motor's fine. Maybe you have to replace the brushes. Again, that's a ramps board 3D printer controller, and then this is my servo controller, PID controller running that thing. So I've done some stupid things with that. We basically made a servo that could lift a human being right off the ground. Strangely enough, nobody wanted to buy that. Nobody has the guts. So if there's anybody out there who doesn't mind being injured by the device that they build and wants to build really, horribly powerful, nasty machines, let me know. The system that I want to talk about today is this other one. I'm going to see whether or not this video switch will work. Now, I want to keep sharing my screen, but I'm hoping that you can see the video of this little unit as well. It's based on the Node MCU, which is basically the ESP8266 from Espressif. And then that's put on a little board with a DC power regulator, and USB interface, and a few other little minor components. These things, the reason why I want to point this out is because these things are incredibly inexpensive. You can buy them in low quantities for under $5 a pop from reputable sources. This is the High Let Go. You can get these for like $2 a pop from unreputable sources. I don't recommend that because I think some of these are knockoffs. I had problems with some of them not working correctly, but I've never had any problems with these. This High Let Go brand is pretty good as far as I can tell. These are also available from like Mauser and other like serious sources now. The Node.MCU is very well documented. For anybody who's not familiar with it, what it gives you is a 32-bit processor, several megabytes of flash memory, and a Wi-Fi RF interface. So the Wi-Fi ability of this thing is just amazing. You think about it, it's $5, 32 bits, megabytes of code space, and a Wi-Fi processor for $5. I don't know if people on the call are old enough, but for an old fart like me, that just completely blows my mind that's just even possible. So yeah, the Node.MCU also gives you a tremendous amount of I/O. There's a lot of GPIO pins. There's some A to D, your UART pins, and and basically you can run ground and VN. They say 5 volts here, excuse me, but that's actually good up to like 9 volts. The onboard regulator is generating the 3.3 that's needed by the chips. So you can run this basically just off of a standard battery pack. So all you really need for this is this Node.MCU, and then you need some RC servos, which can be as cheap as $3, which again is amazing. Or you can run up to like $33 for a super strong RC servo that can, again, get to the point of like lifting somebody. Those are strong enough that you can put them on some kind of a platform and then ride around on it. Then you need a battery, something that's appropriate for the RC servos, 5 or 6 volts, maybe 7, maybe even up to 9, but most of the time that's related to what the servos want, so those are not terribly expensive. A breadboard makes it easy to hook things up. The problem that I kind of ran into with this was you need to be able to connect the servos to the GPIO pins on the processor, and this is true whether it's an Arduino or a Node.MCU or whatever. And so I thought, well, I'm sure that somebody has made a little adapter board that will allow me to, just have one edge of those pins, your GPIO pins on your PC, and then, supply the power and ground bus. It's a super simple little board, and I'm sure somebody has made it. And everywhere I looked, I could not find it. And I was like, are you kidding me? Nobody's done this before? That doesn't make any sense. So I went ahead and designed one myself and got it manufactured. And then there's links in here to go out and get the printed circuit boards from Posh Park or wherever you want. So as you can see, this top header right here is what plugs into the breadboard next to the GPIO pins. Or if you want to, you can work the header support off of the actual side of the Node.MCU and then just solder this board directly to those pins. And then, so each one of those signals just comes down straight to this next pin here, which is the D row here is for the PWM to the servos. And then the middle row here is the plus power supply. And the bottom row is this minus power supply. And there's a nice terminal block here where you can screw in your battery case wires. You can see those in the video link. So you just hook up 4 AA cells or your standard RC servo power supply, and you can drive up to 4 servos with it. So that was sort of a thing that I had to overcome because I figured that was going to be really easy to do. Now, of course you can just directly connect you can take the servo header wires out, and then you can use up 3 rows on your breadboard, or you can solder the wires on or do any kinds of other things. But those aren't mechanically stable, and they're certainly not convenient. So that's why I wanted to make this little board in order to make it a little bit more convenient. So the total price on that then is as little as 16 bucks to have a complete electronics package for your robot, not including the batteries, but including the battery holder and everything else. I think this is a great little project for nieces and nephews and kids of all ages, right? Older kids can get involved in it. So having said that, let's go ahead and do the live demo portion of the program. And hopefully you can see the video there. It turns on. I have a continuous rotation servo connected, which is the one with the disc that's currently moving a little bit. And then I have a standard servo on the other two. Oh, and yes, there are I2C to servo boards, but those are relatively expensive. I mean, I understand they're not terribly expensive. And I didn't want to deal with I2C. I didn't need that level of control, and I didn't want to mess with the cost of it. So that, thank you, Carl, for sharing that, because that is a good alternative to what I was doing here. So once this thing fires up, normally what I would do is I would go up here and I would look for another Wi-Fi connection, and I would find one called Robot Frog. I don't know if you can see, but I have the word frog written on that chip there. What we did was we took a small database of animal names, and we selected one of the animal names from the MAC ID of this particular Wi-Fi adapter. So the reason for doing that is because if you have a room full of kids who are all building this robot at the same time, or a room full of adults, you need to find a way for them to all be connecting to their own robot, as opposed to, you know, this guy over here is driving that guy over there's robot and doesn't realize it. And so having the Wi-Fi ID have a animal name in it just made it really easy to make sure that the kids could identify which robot was which. So I would normally find Robot Frog, and I would connect to it, and away we would go. There's a secret way here where you can get this little guy to connect to your house Wi-Fi, to your standard local Wi-Fi router, and then you can connect to it from your PC, and you don't have to disconnect from the internet. So I've done that already. I already know that the IP address should be this. So hey, look there, we're connected. And you can see that I now have this little control panel. Normally I would be operating this with my thumbs on my smartphone. And over here on this side, we have this little circle which you can move in order to control the servo. So what I'm going to do is I'm going to grab this now. There we go. And what you can see is that I'm slowly moving that regular position servo over, and I'm going to move it back down this way. And then if I do this, you can see the continuous rotation servo is going one direction or the other and going slower or faster. So I have control. Now, normally you would be using two of the same types of servos here. So if you use two continuous rotation servos, this is very convenient, because that's forward, this is backwards, that's left, this is right, okay? But because I'm mixing the servos just to show you the different types of servos are available, that makes it a little bit confusing. The other thing I want to show here is that we have this record button. So when I press record, now if I move this in any particular direction, I'm just going to record a little sequence here so that you get the idea behind it. And now I'm going to go back and stop the recording. And then under this gear, there is, oh, I forgot to mention the trim. You can trim these, the servos here if you need to, in order to get them to stop. So now this listing down here at the bottom is the recording of all of those motions that I just did. This first value here, the 276, for example, is the time in milliseconds. This is the left servo, this is the right servo, and this is the weapon servo. This was originally built for a combat system, so it's called the weapons servo. Basically, it's just servo 1, 2, and 3. So what we're going to do now is, you'll notice that this kind of has a pink background. You can edit it if you want to in order to change this animation. And I'm going to save this into slot 1. You'll see that it turns green. That means that the animation has been saved. And now, if you press 1, you should see in a second the servos start to do, without me controlling anything, exactly the same thing that they did when I was recording that motion. So the point here is that you can record a simple set of motions, and then you can, at any point in time, just play it back. So I'm going to start that playback again, and I'm going to close this. And I just want to show you there's a little status thing up here in the upper right-hand corner that shows you, what mode it's in. It's currently playing back. Once that gets done, it'll go back to idle. If you look at that status while I'm actually driving it, you'll see that it, shows the status is driving. The ping is the amount of time between updates. And what happens is whenever it's in idle mode, it automatically backs that off. So you'll see that number get larger and larger and larger. Right here, you'll notice that there's a 0cm and 000. One of the things I don't have hooked up today, so I'm not going to demo, is you can add a ping sensor, your standard little ultrasonic sensor, and then the distance to an object will show up here and come back into this, this web page. And then these three values right here will also show 3 digital I/O pins. So you can hook up, switches or bumpers or whatever, and then have that data come back over that area. So just to be absolutely clear about what we're seeing here, this is a web page that was served from the Node MCU into my browser. There's no app, there's no software to install. It's just on the actual unit, which is really nice because it's very easy to make changes and immediately see the difference. The other thing, and hold on to your hats, this absolutely blows me away. You can hit edit, and there is actually literally on that unit a file which instantiates an editor in your web browser and shows you the files that are on the robot. So if, for example, we go to index.html, this is the HTML for the thing that we were just looking at. And if I go here and type, I can say, hi, SRS, and I can save that. And go back to this panel and hit refresh, and go into the panel, and there's their ISRS. So this is literally a web dev platform in a tiny little $5 processor. Okay, so I just want to mention real quick that this was made by another member of the San Diego Makers Guild originally, Sir Jeffrey Mallins. The Sir here should be in quotes, but he is a heck of a guy, a very smart dude. And he had initially developed this using, the open source libraries and all that kind of stuff. I see that I'm running out of time, so what I want to do here is jump ahead to information about the sensors. I already mentioned that. I want to kind of show you the flow of information. So the ESP8266 provides a Wi-Fi AP or connects to your network. You can put in this Wi-Fi.txt file here. You can build this file. I'm not going to click on that because that would show you my actual Wi-Fi password. And then once you do that, where was I? Here we are. Once you do that, then it'll connect to your local router, and that gives you your connection to the device. You go to that web page, so that this is your browser on your PC sending a web page request to the web server, which goes into the SPIFFE file folder in the flash on the device. That serves back this index web page. That index web page loads 2 JavaScript libraries, Bundle and Robot. Those both come up off of the actual, again, they're requested from the robot. Bundle.js opens up a WebSocket connection. So then that WebSocket request is then a second server that's on the chip. So there's a web server just serving web pages, and then there's a WebSocket server, which is used for continuous communication. It also, on the web page, there's the user input controls. As you touch those controls, there is in the Robot.js, there's a function loop that's being called. And then that sends the WebSocket data through to ESP8266, which drives the servos. So it may seem a little bit complicated, but I just want to show you that under Robot.js, there is a loop function, which is just like in an Arduino, nothing fancy there. But this loop is what is looking at what the drive stack values are and then sending them on to the device. So you can add JavaScript code in here that does fun things. So for example, one of the things that's being done here is we looked as to whether or not that CM value was populated from the ping sensor. And if it is, then we calculate what our distance is to the object. If we are too close, then it takes the drive stick X value and adds a percentage to it. And then that is what is actually sent to the robot. What that means is that if you try to drive this robot into an object and the ping sensor is enclosed, it will sense that it's getting close to something and turn away from it, turn away to the right, I think it is, in order to avoid the object. And that's just a simple, little example of how you can do development on this device from your PC without having anything extra. Do I have a couple of minutes more, or are we at time?
You're about at time, but go for a couple questions. We're cool. We can.
Okay. Well, if I can just finish really quick, one of the things that we wanted to do here is, if we have a little robot that can run around, it's got a couple of continuous rotation servos on wheels, it would be great to be able to take a cell phone, which is connected to the robot, and set it on top of the robot, exactly the same way that it was Dave, wasn't it, who came just before me? Yeah, David. So you can use your cell phone then on top of the robot and use that as the controller, but also use the sensors that are in the cell phone by writing code, JavaScript code that runs in the browser on the cell phone, served from the ESP8266 to access the onboard hardware like the GPS, the compass, and also accelerometers for detecting bumps or whatever. And also to do image processing, which is amazingly capable in JavaScript in a browser, even on a cell phone. The problem is that the web page has to be HTTPS in order to be able to access the phone's hardware. That's a security requirement that's been added in the last few years by the phone manufacturers, and for example, in the Chrome browser. So what we're doing, you may notice that this device that I'm actually directing my camera at is an ESP32. Which has enough horsepower and is still about $10 from a reliable source, so only double the cost. We should be able to add in a certificate and get even better I/O, and I hope people will get involved and help out with that. So at that point, I will go ahead and stop sharing and switch video and take questions. Anybody have any questions?
As a fellow robot maker, I'm really impressed with what you've done. Your Haddington work. Is this like the playback and record system you've got? Is that going to apply to the Dexter as well for a push to teach?
Oh, so you're asking a question about Dexter. Dexter already has that and has had it from the very beginning. And I'll actually be giving a talk here, I don't remember when, in a couple of weeks. Oh, no. It's in the spring. I'm giving a talk on Dexter. The one I'm giving in a couple of weeks is actually related to this robot as well, but a little bit deeper dive. So yeah, that's already in there. You can grab a hold of a Dexter, put it in a certain mode, move it around, record the path that it followed, and then put it back at home and tell it to play that all back, and it actually works. Yes, WebSocket is used for the sensor data between the controller and the cell phone or PC, whatever it is that's being used. Typically a cell phone, but it could be a tablet or a PC. And so there is a little bit of a delay there, but we're not going super fast. And one of the things that, like I said, I've been completely amazed by is the sensor suite that's available in a smartphone is pretty impressive. And so without even getting the sensor data back from the actual robot hardware, there's all kinds of sensor data that's available to a HTTPS web page to be used for making the robot smarter.
Use blink.io, blynk.io, and it's pretty nice. You just add a library onto the ESP, and They've changed their pricing though, so I'm not sure it's as advantageous as it was. But yeah, that gives
Yes,
you that
it is.
whole phone connection and everything through their servers.
Yeah, so yeah, I was about to say, correct me if I'm wrong here, but and Blink is cool as heck. I don't want to try to pretend that it's not. The problem that I have with Blink is that it is proprietary. It depends on their servers. This does not. It's just direct. It's not going to the internet and then back to your cell phone. It's just direct to your cell phone. So you get a much faster response, number one. But more than that, when that company goes out of business or decides that they don't want to support that particular thing anymore,
Or raises the price, yeah.
or
Right.
raises the price or whatever, you're toast. This system is completely open source, or as open source as it possibly can be. And it is somewhat future-proof. Web browsers are going to be around, JavaScript's going to be around. Cell phones are going to have all those kind of sensors in them. And, the ESP8266 and ESP32 are certainly not going anywhere anytime soon.
Can you post a link to that library? It looks really cool. I mean, being able to edit the web pages and all that directly is pretty nice.
Oh, yeah. Right. Yes, I meant to do that.
Thank you.
I did not grow up in New York. I've never actually been to New York, and my son lives there, and I need to go visit him. He's graduating from Stony Brook University in December, and my lineage has been traced back as far as Giles Newton, who came over in 16 something or other, and then later fought in the Revolutionary War. He and his two sons did. And they were granted land in Marlborough County, South Carolina. And so, yeah, that's more than you wanted to know. Nobody knows. Isaac Newton, as far as we know, never had children, never married. However, his brother did have kids somewhat prolifically. And so there's a possibility of being, related to him.
Okay, thanks,
Thank you, by the way, for letting me present all that.
Yeah, thanks, James. Okay, let's go ahead and move to Fred. I'm not quite sure how to pronounce your last name.
Carefully.
Yes, Douthit?
Hi.
Oh, muted. Fred, we lost your audio.
There we go.
Anyway, I'll hand it over to Fred, talking about what is rovers, drones, satellites, navigation, and more. All yours.
I'm here to.
You lost
My
audio.
audio is going to fight me. I'm here to answer that burning question today. So rovers, drones, satellites, navigation, and more is a group of robot enthusiasts who meet on a regular basis to talk about, build, and run micro-autonomous vehicles. MAVs can look like a lot of the other vehicles you're familiar with. They often reuse existing radio-controlled cars, planes, copters, boats, and submarines. How do we compare to other robotics groups? Well, much like the other robotics groups I've formed, we're affiliated with Robot Garden, a makerspace out in Livermore. And actually, since 2015, gosh, I've created a number of different robots. I understood that at the start of this, they wanted to hear a little bit about pedigree. So let me give you that in 30 seconds or less. We started doing two-wheel differentials, moved into larger two-wheel differentials, did an RC Robo-Magellan with X-Max 36 by 24 inches by 24 pounds by 60 miles an hour capable. So we love our rovers. Rovers and Drones is not a show and tell event as compared to the Robot Hour, which I host at Robot Garden and meets every other Saturday. Our events are focused on troubleshooting builds. We encourage our folks to come to the meetings with their problems and questions. We're fortunate to have a few folks with experience building maps. This is different from, sorry about that. This is different from other groups in that we actively keep people from falling behind. We have a 2-week cadence. We basically meet every other Tuesday. In regular meetings, we encourage this mic is going to fight all day, I think. We encourage people to work on their projects in the 2-week intermediate.
We actually lost your audio again.
Entirely? How's that? Can you hear me?
really, really quiet now.
How about that? How's that?
Still really quiet.
Okay, we're gonna go back to the webcam. Okay,
There we
we'll
go.
see if we, we'll see if that can't be convinced to work. We have a 2-week cadence. We meet every other Tuesday, regular meetings. We encourage people in the interim to work on their project and bring their questions to the group, show off their progress. Okay, well, maybe there's a little show and tell. But now let's get back to the bots. Autonomous vehicles are designed to operate on their own. The types of vehicles include, of course, the copters, etc. While there are differences in the hardware that we use 2 primary components, a ground control station and a flight control computer. Our ground control station consists of a computer, antenna, and software. Ground control station software can be run on a PC, a laptop, a phone, or even an RC controller. The antenna allows the ground control station to communicate with the MAV's flight control computer, again, FCC. Now the drone, or MAV, has a flight control. Is that working still? Wow, that's weird. The flight control computer that we already talked about, an RC, and of course, the antenna to let the 2 communicate. Autonomous navigation is primarily accomplished by using the flight control computer. We use a Pixhawk for reference, though there are a lot of other manufacturers. And of course, there are a lot of other sensors and actuators that we use, satellite, GPS, or more accurately, GNSS, receiver, compass, accelerometer, battery monitor, arming button, a buzzer to indicate status without visuals, and hey, out in the field, it's nice, it's hidden in the grass, an RC radio interface, and a GCS, or ground control station radio antenna. So that's mainly what we're using as far as components. We actually are based on a Pixhawk Ardu Rover style design, and you can pick up the components, the major components to build this thing outside of the RC for something just south of $200 from Amazon. Additional parts that you may need are lithium battery for the electronics, a charger, an RC car, of course that could be a plane, and a transmitter controller. You're going to need someplace to put these parts. Now, one way is to just simply use, especially if you're doing a rover, a big flat surface area, because wow, that's easy to tape onto. I use 8.5 11 by 11 as an example, clipboard size. You could use an 1/8" ply, or you could just use a clipboard. Temporary fasteners, double-sided tape, 3M wall fasteners to hold the components down, extender RC cables depending upon the size and gender as determined by your robot. And of course, a micro USB to USB-A cable. Pretty simple stuff. Let's now think about ground control stations. What is a ground control station? Well, in one sentence, this is going to be a big one. A ground control station allows you to plan, program, configure, control, monitor, analyze your drone. But let's unpack this. That was a lot. So you can plan. You can plan missions. A mission essentially is composed of waypoints, which are latitude, longitude, altitude. Notice this has kind of a eye towards using copters or drones. And these waypoints can be actually manually entered onto point and click onto a map that's actually integrated. Google Maps, Bing Maps, OpenStreet, number of providers. It's integrated directly into the ground control station. So very convenient. You can control the rover using a ground control station. You can select mission commands, drop-down menus, starting a mission, holding, return to launch, manual control, that sort of thing. Gives you a lot of control. You can configure, and oh my God, there are so many. You get drowned in the number of configurations, the number of alternates there are. There's over 300. So, but those things allow you to change, add additional sensors, cameras, control PID algorithms. It's endless. Analyze. Analyze is one of the coolest things. You can download your mission logs, and this Ardu Pilot software keeps track of your mission. You can download those mission logs, analyze them directly in your ground control station. So kind of an all-in-one solution. Moreover, you can do software in the loop simulation. So you can exercise your software in some virtual environment or replay your past glory. Fun, huh? So ground control stations communicate, as I said before, to flight control computers using a radio. And of course, these ground control stations are written for Linux, Windows, and Mac. The ground control stations talk to those FCCs, which is also known as an autopilot. Well, that's pretty cool. Assembly is relatively simple. Most of the components, and you can actually see them to the side of my head, most of the components are plugged together without needing to be soldered. Components can be mounted directly on the clipboard platform using tape, fasteners, etc., whatever your heart's content. Attaching your clipboard to the RC platform, well, that's a little bit more tricky because there are so many RC configurations. Kind of cool stuff, though, let me tell you. So what are our future directions? Well, adding a companion computer, such as a computer that runs Linux and ROS. Typically, we interface our flight control computer and our additional computer on board using a 2-wire serial and the MAV protocol, Micro Autonomous Vehicle Protocol. That's the same protocol that the ground control station actually uses. It's kind of neat. As configured, our vehicles understand the environment as a map. So the basic vehicles don't understand things like walls, people standing in the way. Don't worry, there are additions that can handle that. But the initial vehicles, in terms of this particular build, are really not all that sophisticated outside of the fact that they can do global navigation, that little thing. With cameras, LiDAR, radar, other sensors, our rovers can be in touch with the environment, and heck, throw in machine learning because everybody loves that these days. So lots and lots to do. As somebody earlier mentioned, wheel encoders with Hall sensors, tons and tons, dead reckoning is possible. Sky's the limit. Another thing that our members have expressed interest in is RTK, or real-time kinematics. Our satellite gear provides a degree of locational inaccuracy up to several yards. RTK has the potential to bring that inaccuracy down to the centimeter level. Another fun thing that I'm looking forward to is a custom board for semi-custom needs. So we're working on a board which merges a continuous power supply. If you know anything about RTK, you'll know why you want that. A power bus, a microcontroller, and a bridge that makes it trivial to connect the antenna out from your RC to the Pixhawk, and then back to your motor controller and to your servo. And of course, like everyone else these days, we love taking a look at other people's layers and labs. And we look forward to having competitions within our club and larger competitors. I mean, these are, after all, Robo-Magellan style vehicles. So that's a popular thing. Does this interest you? Want to build a rover, but could use some help? Drop by and check us out. Look for us on Robot Garden's calendar. Check us out. Check out the Arju rover designs at arjupilot.org/rover, or watch our videos and bots and other fun stuff, Robot Garden's video channel. I'll paste those to the chat. And thanks for listening to me today. Do we have time for questions?
Yep.
Ooh, looks like we have a few.
Yep, you got about 10 minutes for questions. Go for it.
Okay, I'm going to paste those. They're my links. And, it's hard to roll back. 10 minutes left in the talk. Okay, cool. I tell you what, why don't you, rather than me trying to roll back and look silly, go ahead and speak those questions out.
Anyone,
Is
just
there
go
any
for it.
opportunity for people from outside your physical area to be involved in this?
I'm actually up here in Mendocino County. Robot Garden is down in Livermore. One of our guys is in Arizona. We have Donna's come to a few meetings. So yeah, we get people from all over. So we're certainly open to that. Very much so.
Yeah, your mic dropped out again.
Please come join us.
Don't you
We're
just
open to all.
Don't you love technology? Nice job of sticking with it through your mic going in and out. I love it. If you get a
I
chance,
hate to
can you
admit
post the
I
link to-
have practice.
Are you going to post the links to the thing in the chat so we can see the?
I already did. I already did. Should I post it again? Oh, I was posting the wrong
I'm not
thing here.
seeing the link
Yeah,
there.
you might be posting it just to me.
I am sorry about that. I guess I was responding to your post inadvertently.
We see it now. Thank you.
Other questions? Well, good. Thanks. I really appreciate it. Thanks again for inviting me. I really appreciate it, guys.
Okay, thank you much. At this point, we've gone through 3 presenters. We have 2 more to go. Let's take a 15-minute break. Actually, yeah, let's take a 15-minute break. I will pause the recording and put up a timer. And we'll be back in about 15 minutes, and we'll pick up Dan Royer and Jim Kindsvater. Geez, Jim, sorry, I can't pronounce your name. Talk to you guys in a couple.
So are we free to chat amongst ourselves during this break?
Oh, absolutely. Yeah, go for it. Yeah, and if you want to do more Q&A from the prior sessions, absolutely.
So I'm just curious, Fred, how many the system that you're doing is both rovers and.
Okay, folks, welcome back from the break. Next up, we have Dan Royer talking about spot micro simulation. So all yours, Dan.
Hi, gang. Glad to be here. My name is Dan Royer. I live in Vancouver, Canada. I've been making robots for about 11 years now. My first robot was a crab that walked, and I was so ignorant, I didn't know I couldn't do it, so I succeeded. It was about a 6-week process. Through a long series of other robots, I've kind of looped back around. You've all probably seen the Spot Mini that made by Boston Dynamics. It's a gorgeous robot, and like most of you, I said I want one of those. I wasn't able to buy this one, of course, but I did find this one called the Spot Micro, which is a gorgeous little robot and very printable. And they have some simulations, again, in ROS. So in some of our talks with some people, we've discussed how hard it is to get ROS running. And in the Spot Micro world so far, the walking gait looks a bit like this. This is like the state of the art in Spot Micro. I'd like to point out that if you watch the Spot Mini sometimes when it's walking, as it starts to walk, you'll notice that it bounces its feet. See that? So it kind of does the same thing. They have a pattern of hopping before they go into a forward motion, and it's decidedly unnatural, I think. So I have I may be getting ahead of myself. I printed out a set of the parts, and with a group of students from Alpha Secondary School in Burnaby, they've been documenting their progress as they've been assembling it, and their discoveries as they learn about the servos, and they've been learning about Arduino programming, and some of the challenges like assembly and 3D printing. They've even gone so far as to make, down here, they've got a test harness so they can start working on locomotion. And we quickly discovered that the cost of burning out a servo is quite high. So then we were looking around and we saw that there are some simulators like this Unity. This is supposed to be an agent training walking motion. What I'd really like to get is more like one of these SIGGRAPH papers where the walking is absolutely gorgeous and looks totally natural, but I haven't been able to find links to any of this stuff. So I got to do it the hard way and basically make my own. And it happens that I have an app already called Robot Overlord that I've been using to simulate my robots from the beginning. I taught the crab to walk in here, and then I copied the code into the brain of the robot, and it worked. I do this for the robot arms that I have now. And I built a small simulation of a dog that pretty much walks the same way as this sort of hoppy motion, right? You can see here there's target points on the feet, the destinations, right? And animation sequences, and there's a triangle on the ground that is the polygon, like the center of mass, right? As long as you're inside the center of mass is inside that shadow, you don't fall over. But there's no physics in here, so it's missing that from the why my words failing me. It can't fall over, and if it can't fall over, we don't know if our walking is actually going to work until we put it in the real robot. So personally, I feel that that's still too expensive. So I tried writing, I started working on some basic physics stuff. These are several experiments that just explode. I've had cubes and spheres and other things in here that don't work right. And then I decided to take a step back and move to just 2 dimensions. Basing the work off of a library called Impulse Engine by Randy Gall. Starting to get some 2D physics to work. This is in processing, so it's Java based. Most of the work I do is in Java because I don't want to have to set up a Linux partition, and I don't want anyone who wants to use this to have to set up a Linux partition, which is a large part of that ROS OpenCV headache. I would also like to see more robots using Robot Overlord, and more people. I'd like this to become a household name in this community and people to be able to work off of this with a minimum amount of pain. That's my goal. I'm trying to help other people in that way. So the attempt here is if I can get 2D physics working. Oh, you can't even see my screen because it's all blown out. Let's try this. If I can get 2D physics working, then I'm hoping to get to translate that into 3D physics after that. I'm hoping it's only one dimension to add. And then the earlier version that you'll see will work better. And then we can have a dog that falls over realistically like a rag doll. And then we can teach it to walk. And then we'll get more natural looking motion from all of our vehicles, really, including walkers. So how do I now turn off the screen sharing? Okay. So some of you might ask, well, why didn't you use a commercial library? Because I'm working in Java, the only libraries that I've been able to find are either like 4 years since their last update, and their maintainers are unreachable, which I feel like leaves an opportunity in the market for somebody. Why not work in Python? Python is a great language. It's supported by a lot of people. If show of hands, how many people have more than one version of Python installed because they're not really backward compatible? And there you start getting into that same ROS shaving the yak. You have to go through a lot more steps than necessary. And that's not cool to me. What else can I tell you here? Yes, so my project has been my goals right now are to get a 2D physics library working in processing, then copy that over into Java and hopefully make that library separate. So anyone who wants to make a game or do something fun with physics, try something simple, will be able to. And I'd love help from people who are much better at math than me. And it's not hard to be better at math than me because my math actually ends in high school calculus. I'm currently working, I'd love some help on building constraints. So making a pin joint in a knee of a leg, for example, or other forms of linkages so that we can tie these physical shapes together and then make them do fun stuff. We get way closer to the fancy demos that we've seen in some of my examples. And I'll post all the links into the conversation in the chat. Once we get the 2D library working, I want to do the same thing in 3D and then put it into Robot Overlord. So even the robot arms will be physically simulated, and we can understand things like gravity and how much lift. Yes. So I don't have much more to say. That was my plan. That's where I've been at. That's where I'm heading. I have lots of other robots if you want to hear about them, but that's the one I wanted to talk about today. Please hit me with any questions you have. I yield the rest of my time. Thank you very much. If you want to read more, I'll say one more thing. If you want to read more about the work I'm doing, you can check out my blog every Friday at marginallyclever.com. I post a Friday facts post with news about all kinds of stuff. The last one was about using this large format printer back here to do sewing patterns, which I had never considered and apparently has excited a lot of people. Thank you very much.
Okay, any questions for Dan?
If nobody else has a question about the Java simulation stuff, I'd love to hear about that 2D robot on the window behind you.
That robot is called a Michelangelo. It is a wide format printer, a plotter. It's currently, this model here is 750 millimeters wide, so it does a A2 sheet of paper. And I have in a box that I can see from here, I have the next version, which is the Michelangelo Huge. Out of the box, it's the same as this guy, and you can buy an add-on that makes it twice as wide. It'll come with extended belts, so you could do, what's 4 times A2? That's A0, 2A0, I think it is. It's big. It's really big.
So that's actually a kit?
Yes, it comes fully assembled. But when I say kit, because you can add the bigger piece. The plans are completely open source, so if you want to download that, you certainly can. There's a version of Robot Overlord called Michelangelo Software that is completely open source and runs the robot. And not too long ago, we actually replaced all the firmware in the robot with a version of Marlin 3D printer firmware. So if you've had any experience with that, then you're already ahead of the game. And it runs smoother and faster than ever before. Plus, it's one less piece of code I have to maintain. A lot of what I'm doing right now is learning to delegate, especially with these students. And because I'm just I got too much to do and I'm trying to go faster. So I'm looking for all the help I can get.
Just out of curiosity, have you looked at like 3JS and some of the other three-dimensional physics engines? I'm trying to think of the one, Bullet, if I remember correctly.
JBullet is the Java library. That's the one that I mentioned. It hasn't been updated in 4 years. Yes.
Yeah.
Well, 3JS runs in a browser, and I understand you can set up a thin client and do this whole thing. It's not my forte. It's not my comfort zone. And I've hired students from the Center for Digital Media in the past to build me such a system. And then afterwards, when they were done, I was like, this is great. And I can't even read the code. I don't know how to maintain this, and I can't afford to keep you on. So, and they weren't willing to volunteer.
That blows my suggestion, because what I was going to suggest was looking at the source code for like the JavaScript version of Ammo. I think it's ammo.js is the one that's currently alive. 3JS uses it or something like that. I was just wondering if looking at some of the working JavaScript source code would help with the development of the Java code. But
it might.
Yeah, reading other people's code can be a very difficult thing. So I appreciate that might not be a good suggestion.
Impulse Engine from Randy Gall was written in C++. I can read other people's code, and I'm not against it. But it was the act of maintaining the JavaScript code in the thin client, that was too difficult for me. I'm actually I would like to see a day where I merge Robot Overlord and Michelangelo software into one app, so that there's even less. Maintaining 2 projects instead of 1 is harder. Yes, simplify. I love to tell people that I've got a robot arm. Version 2 was 1,300 parts in 250 types. And the next version that's right here is 250 parts in 25 types. Simpler, 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 simpler. Yeah.
Okay, any other questions?
Hey, Dan, this is Donna. Could you post in the chat for everyone all the relevant open source and related links for the various tools that you've been talking about throughout your presentation?
Here we go.
Okay. Okay. Thank you.
Some of those should have GitHub repositories. Some of those are YouTube videos with examples. I hope I've given credit every. Oh, I also want to mention, I meant up here and here, there's Rodog. So one of the challenges with the current Spot Mini is it's wide and flat. So it's a very squat body. And that means that on the occasion where it falls down and it lands on its back, it's stuck like a turtle. And I would like to see it redesigned with a curved back and a tall, thin body. So it's not quite my brain keeps wanting to go to a lifting body like an airplane, but that's not the right phrase, but it's a bottom heavy self-righting model so that it's much easier to get it back on its feet in the case of an accident. Rodog is a great example that's on Hackaday, and the link was back up in here. Yes, this one. And it is gorgeous. Rodog. There it is. This cute little guy has many advantages it prints with a lot less support material, it prints faster, it's stronger around the major joints, a lot of things like that. It doesn't have every feature I'm looking for, but already a big step up. And the developer for the controller in there is an active member of the Marginally Clever Discord group. So we've got a growing number of robotics people who don't just meet on the weekends. And so if you're in the middle of something in the middle of the week and you need help now, come and talk to us because we're there 24/7. Yes, a big community growing in Germany has come out to join us. So basically around the world all the time. And that's cool. Thank you.
Okay, with that, why don't we switch to Jim? Thank you, by the way.
Thank you.
Jim, are you still there? Oh,
Sorry about that. I always tend
sorry.
to unmute. Can you see me now? Because I can't tell when I'm speaking. I get the last person up.
Now, hang on a sec. Let me see if I can. There we go. Now we got you.
Oh, yes. The host has spotlighted my video.
Sorry.
Boy, do I need that.
It's my job.
My name is Jim Kindsvater, and I'm a semi-retired engineer and been in Seattle Robotics about, 20 years. I can't really remember when I joined, but it's been a while, that's for sure. And I really have enjoyed all the meetings I've been to and look forward to getting back to them. But even this is better than no contact at all. So give you a little background. I've been building robots for about that same amount of time. Actually, my whole career was building sort of RC controlled things, but they tended to be a lot bigger, like tunnel boring machines and stuff like that. But I've been very interested in robots, and especially in robot vision. And some 20 years ago, I first started looking into that, studying the stuff that Jim Wright was doing at that time, using just really simple 8-bit micros and trying to compare and contrast, and therefore do distance measuring of two different video signals. It was pretty awesome code for the time, and I've been ever since trying to figure out how to do vision. And I finally stumbled on the Jetson Nano a couple of years ago. And that's about a little while after it came out. And I brought it to a meeting and kind of talked about it. And as with most of my projects, I haven't put as much time as I'd like to into it because, gosh, I've got all this other living to do and a wife that wants me to say hello occasionally. So it's been kind of interesting. But anyway, over the last few days, I've kind of summarized what I've been working on in a little video that I'm going to present now, hopefully. And it's a little choppy because I'm kind of still learning how to use all the new tools I picked up, like a new mirrorless camera and video editing software and stuff like that. So I hope it works for you. It's only 10 minutes long. So if it doesn't work, why tell me, and I can come back to talking like this. Anyway, I'm going to share my screen and let's see if I can make it work. Well, that didn't work. Okay. To the Jetson Nano JetBot robot. This is my version versus the original version, and it has some significant changes. Here's a kind of a close-up view, but I'll set it down on the desk and we can look at the individual features. Here's the Jetson Nano laid out on the desk for you to see what you can see on that. As you can see, it has the Jetson Nano CPU on top. If you're not familiar with that product, it's a 128 core steroid version of the Raspberry Pi. It also has 4 gigabytes of RAM and runs at over 100 megahertz. It's a pretty fast little processor. It has the capability of running ROS or TensorFlow or many of the modern analysis tools that we can use to work with vision, and that's my interest. I first started getting interested in vision about 20 years ago, and I've been pursuing this as best I could all this time on a part-time basis like we all do. I'll discuss that a little bit more in detail later. Let's look at the robot. So as I said, the Jetson Nano is on top. Unlike the regular JetBot, this particular Nano has dual cameras so that I can try to do range finding and by comparing 2 images. On the bottom, it has 2 of the drive motors and a drive card. It's also equipped with dual Wi-Fi antennas so that we can communicate with it via Wi-Fi. And on the back, it has a small OLED display which displays the Wi-Fi address. And in the front, we have a full pan and tilt mechanism, which allows us to focus the cameras wherever we want to. And just below that and behind is the drive board for these products. Any of you that have used the Raspberry Pi are acquainted with the complicated setup that is required to program it and interact with it. Normally, you have to hook up an HDMI cable to the Raspberry Pi or to the Nano to activate an attached monitor. Then you have keyboard and mouse, and it's basically like working with a regular computer at that point in time, although of course you're programming in Linux. So what NVIDIA has done is they've come up with a alternative programming method. It's commonly called headless because it doesn't require all these connections, but the connection is made over the Wi-Fi network, and you can program and interact with the robot without all those wires via the Wi-Fi connection. Basically, they set up a Wi-Fi hub on the robot that you can connect to with your computer and use the Jupyter Lab setup to communicate with it. Of course, the big advantage of this method of communication is that the robot is completely independent, or can be independent in its operation. The way to find out about all of these features is to get on the internet and Google Jetson Nano JetBot, and you'll be taken through a series of connections to the JetBot wiki. There they have a complete assembly guide of how to put together either your own kit or any one of a number of kits that you can buy. It's easy to buy a kit from SparkFun or a number of other people for about $250, which contains the Jetson Nano and all the parts that make the robot. That robot will only be furnished with one camera. And since I wanted to do range finding, I added 2 cameras to my setup. As part of that wiki, there are a number of examples that you can run. And this morning, we're going to try to run one of them, which is the object detection and avoidance example. And a little while, I'll show you how you program it and the results that I had. In order to program the JetBot for obstacle avoidance, we have to give it a number of pictures, both blocked and free. And here's how we set that up. Here you can see the setup of my robot ready to record images for the blocked and free frames that are used in the actual search engine. Right now, it's being set up for a block, and I'm actually going to go with the computer there on the right and hitting the red box. Now I'm going to back it up for a free picture and click on the green box. The free is trying to delete the blue tape from the picture. And if you look carefully at the laptop on the right, at the top part of that screen, you can actually see that the picture that's being taken is being shown just for reference on that little picture format there. So I actually did this about 100 times each for blocked and for free setups. And that's about the minimum that you can actually do. It took about 10 or 15 minutes to do that. Obviously, this is the speeded up version of what I did. I'm not quite that fast in movement, but I did manage to get it done. I did figure out later on that it was a lot easier to take a whole bunch of block pictures at one time than it was to do, and then do free pictures again. So that's how it finished off. Once we've entered all our blocked and free pictures, we follow the directions to submit them to something called PyTorch, and from there to a modeling system called Alexa. I don't have time today to, not Alexa, AlexNet. Yes, sorry, there got too many Alexas around my house. Anyway, Alex is a system that has been set up to analyze 1,000 different cases, whereas we're just analyzing 2, but through a method which I honestly don't understand, you can kind of piggyback onto that original analysis and make your own and add your own features, make your own analysis to make this system work. Once you go through all this analysis, you'll be able to find what they call an optimized model, which you can then control the robot with. And so here are the results.
There's something there. Yeah. Too bad.
So when I stopped laughing after that thing went over the edge, I actually could consider that a failure, or I could consider it at least a partial success. To me, it's actually pretty amazing that in the maybe 0.2 of a second between the time that the robot sees the line and actually decides that's not a place I want to go, it can actually make that decision, all the while doing a lot of calculations that I can't even imagine. So at least for now, I feel pretty good about the fact that yes, it can be done. I got a lot of work to do. One of the things that the previous model had, which I didn't have, was a speed control. For some reason or other, I took that out. And if I could have turned the speed down a little bit, I think my success rate would have been a lot higher and I wouldn't have had to chase it quite so much. But oh, what the heck, you gotta, nothing ventured, nothing gained. So I was really happy with that. My plan here is to try to analyze the code and add that speed control back in, and then further my studies into how this whole thing works. I'm basically, I should say, a hardware guy. I like building robots. I like soldering boards together. I'm not a software maven. I need somebody like Donna to guide me through all this. But I am slowly learning how Python works, which is how you program this stuff. And I'm hoping to get to the point where I can compare those images from those two cameras with find important features in each one of them, compare that, and then do some ranging in my effort to navigate the thing in the future. And so this is just a little robot to start with, but it shows me that at least it can be done, and that it's a $100 processor. I'd like to introduce you to the Jetson Nano Web-Bot robot. This is my version versus the original. I think I'm stuck in a terminal loop. Sorry about that. Anyway, I guess that's about all I have to say. So if you all got any questions, I'd be happy to take them on.
Okay, just pop up and yeah, go for it.
I'm sorry, I'm not hearing anything.
Nope, sounds like we don't have any questions. Last call for questions for Jim.
I'm curious what that setup basically costs.
Well, my version, I had some advantages. Like I say, if you built that from scrap, from a kit, you have $250. That's including the Jetson Nano. You can buy, if you get on the, like on Amazon, for example, they sell $150 kits, but they don't have a Jetson Nano, which essentially is $100. So about $250 to get to you to do that. If you want to do my version, you'd have to send me an email asking me to send you the 3D printed chassis that I came up with to mount the servo so I could have pan and tilt, and you'd have to add another $25 camera to it. And then the pan and tell mechanism was about $20. One thing I forgot to refer to in that whole sequence of events was a guy on the internet called Paul McWhorter, who has a website called toptechboy.com. And he does a fabulous job of taking you through the idea of object detection and, I don't know, face detection, all kinds of different uses for the Jetson Nano as a desktop, on a desktop basis. He's got like 60 hours of lessons where he actually develops the program. And I've learned just a ton. I've actually only been through about 30 hours of it because I did that and then I decided, oh, well, I want to build a portable robot. So I need to figure out if I can do this on a, you know, independently of being all wired up together. And so I kind of got deflected from that. But now that I figured out I can, now I got to go back to those lessons and, you know, really figure out what the code is doing. And it's actually, you know, as always, the YouTube is just an enormous resource. There's not a whole lot on the Jetson Nano up there because it hasn't been out for a long time. If you want information on the Arduino, my gosh, it must be 1,000 different people posting to that. This one's a little more powerful, and I'm glad because I think it has the capability to actually do this stuff in real time. But again, you can buy any number of kits. Like SparkFun's a good point for like $250. That's kind of an extended answer, but there you go.
So are you considering sharing the STL file for the base?
I'd be happy to do that. Where should I put them? Should I put them up on Thingiverse or how's the best way to share?
Thingiverse is great for me. You know, everybody has their own favorite thing. Other people like GitHub is cool too. If you're going to add some code or stuff like that in the future, maybe a GitHub project would be great. I would love to see that sort of thing. The other question I had was, how long does the battery last?
Well, I don't have an answer for that yet because I haven't run it very much, obviously.
So at least what, 2 minutes?
Oh, I mean, I've been programming it quite a bit, and it's, you know, I've got to say I've got an hour in programming because programming doesn't take much power. The battery pack is a 10,000 milliampere hour, one of the standard little battery banks.
Oh,
I absolutely love that thing because it gives you a, you know, it's got a little digital readout on it, which tells you how much time you got left, which is
those are nice.
Really nice. That's the first time I've ever actually been exposed to that. And it's a great way to power a robot.
So it sounds like it's not sucking the battery dry in no time, is the?
No, it's not. And as I say, I haven't been able to run it a long period of time. I'm gonna guess it would run for at least 20 minutes in a combination of programming and running, because that's a lot of power in that little battery bank. And that, again, you can find all that in the Jetson Nano robot or the JetBot wiki.
Jim, could you please put your relevant URLs that you've been mentioning in the chat itself, especially that 30+ hour related training resource that you were talking about, and also some more Jetson Nano either purchase or documentation URLs? That would be fantastic.
Okay, I'll do that.
Hi, Jim. This is Dave. So I have a question on the vision aspect. One thing that I'm working through is varying lighting conditions. The robotics I do is outside. You know, the sun moves or things change. How do you think that that Jetson vision would? Do you have thoughts on how that works, and maybe that's a potential solution there?
You know, that's something I've spent a fair amount of time looking at, and I don't have a really good answer because, as you've pointed out, what's blue to your eyes in the inside is green in the sunlight, and it's an interesting challenge. And theoretically, if you train this thing well enough, it will adapt to all those different conditions. I guess I should refer to a project I'm working on at work. Right now, I'm working for a little company that builds drones. And we are working with a group of students at the University of Washington that have developed a program using the Xavier, which is the uptick version of the Nano, where they've taken 30,000 images and trained their model to look for people in the woods. What it is, it's a search and rescue tool to be used with a drone. If you want to find somebody in the woods, you send a drone out with it monitoring with an FLIR and a visual camera and this program, and it does a pretty good job of finding people and separating them from forest and separating them from dog. For instance, they had a video that they showed us as part of their demo where they had a group of people and a dog was walking with them, but when the dog walked away from them, the box did not include the dog. You know what I mean? The way they show that they've identified these things is it draws a little box around them. It's pretty common in vision to let you kind of troubleshoot what you're doing. And it's very impressive. And they've done it in sunlight, they've done it in dim light, they've done it at sea, they've done it at, a whole bunch of different conditions. Now, mind you, they're using a processor that's, I'm going to say conservatively 100 times more powerful than the Nano is and costs about 8 times as much. It's about $800 for a Xavier. But the potential is there. And what I've done is I've trained 100 images. The more images you train, theoretically, the more accuracy it can do. In other words, as you were saying, Dave, train in sunlight conditions, train inside, train in twilight, do 1,000 images in different ways, and then find a really good GUI processor to do that model. Because when I just did my 200 images and they were done actually on the Nano, it took about 45 minutes to go through there and analyze all those images and actually develop the best case scenario to use controlling the robot. And you can see how well it acted. And that's in one lighting condition. So you better have, they do give in the wiki a way to download your model to a more powerful computer like your desktop. Although, as I mentioned in there, you got to be kind of careful about what you do. It's one of the things that's frustrating about examples like this is that you can follow them exactly and shoot yourself in the foot. So you want to do as much research as you can to find out when you shouldn't follow them as when you should. Because if you follow that wiki exactly, you will do that. It's actually a compression routine. And when you do that, you foul everything up. So you got to go back to the step before you do that and not take that step. And then you can make the model actually work. It took me about 2 weeks to figure that out. And it was somebody else on the internet that actually told me that. But anyway, I think I've varied away from it a lot. That I believe the answer is make your model more robust. I'm not sure if you're going to need a more powerful processor, but if you're, for example, using your PC as you do, you've got a more powerful processor. So it's very possible that you could run ROS or even run this software. I'm not sure how well it works on a PC. I've never actually tried it, but if it's an engine running Linux, it should work fine. So if you could get a Linux computer and do all this stuff and do a robust model, I think it would be much more accepting of the varying lighting conditions that you referred to.
Yeah, I think you're right with more data. And from a compute perspective, I think the Jetson actually has more compute capability. It has a lot of parallel processors from what I understand. So
yes.
Yeah, it's cool tech, man. Thanks for showing.
Okay, folks. Well, at this point, let's see. Move that. Donna, you wanted to make a couple closing remarks, so I'm going to hand it over to you.
Okay, thanks, Lloyd. And thank you so much to yourself for being our great host today. I very much appreciate it. And one final reminder there to Jim, please include those URLs that we were just talking about for the tools. That would really help. Thank you. So in closing, as your event coordinator for today's event, I want to truly thank each and every one of you for both attending and especially to all of our great presenters today. I think it's been a great information exchange and resources sharing event. And that was my overall hope for what was to come out of this event today. So I very, very much appreciate everyone's attendance and participation. And also, especially for all you non-SRS people, I want to invite all of you to go to our club's website, which is seattlerobotics.org. Check out the details for both whenever we go back in person, as well as this continuance with virtual meetings. I want to invite all of you to continue or to start attending our regular club meetings, which are held on the third Saturday of each month, starting at 10 a.m. Pacific time. And so I want to encourage all of you to start attending those and to stay tuned for at Robothon.org for the main homepage is where we announce all of our upcoming events, whether they be in person or follow on virtual events like what we have done today. And so stay tuned on Robothon.org for all those kind of details. And again, Lloyd, I want to thank you for hosting this event today. And I want to open up the floor for any logistics or follow-on questions to myself.
So Donna, thanks much also for all your efforts in doing the advertising and pulling together the speakers and all that. That was wonderful too. So
thank you.
Donna was doing a lot of the stuff kind of behind the scenes on this and coordinating.
Thank you very much. Appreciate that.
The other one is if folks want to hang out after the meeting. I think at this point I'm going to go ahead and stop recording.
Actually, Lloyd, I recommend that you go ahead and you keep recording going for at least for a little while and see if we get more participation with further on comments and questions specific to our presenters. And then maybe beyond that, then go ahead and terminate the recording. But let's just see what happens with additional stuff.
Yeah, I can keep running until about 2:30, and I'm recording this to my local machine, and then I've got to depart.
Okay.
But folks are welcome to hang out, until after that and go for it. And yeah, so at that point, I guess we'll wrap the official session and begin the unofficial session. So thanks everyone for attending.
Thanks for having us.
Thank you.
Thanks, guys.
What is onlinemetals.com?
What is what? I didn't hear the question.
Sorry, that's Jim trying to find some links. That was another one of those erroneous verbiage things.
So I remember getting one question from someone during my talk about how I hacked the robot. Is that person still around? I could go into a little more detail if you're interested.
If they're not around, I'm interested in hearing.
Oh, sure. I mean, so essentially, the RC car works off of pulse width modulation, and so it just has a standard hobby servo which turns the wheels left and right, and so you send it a pulse width modulation or PWM signal, and that typically comes from the radio receiver, which you have a radio controller. So instead of plugging the steering servo into the RC mechanism. You plug it into an Arduino, and Arduino is really good at sending pulse width modulation. And so that's how you essentially hack the servo. You can control it with the Arduino. And it turns out that the motor controller, which regulates the speed, it's also pulse width modulation. And so you just, that's how you do it. You just plug it in to the Arduino, and then the Arduino can regulate that pulse width, and you're autonomous. So.
Yeah, so it's standard RC stuff, right? Nothing unusual about it, other than just that you're making the Arduino pretend to be an RC receiver and put out the PWM signals in the standard RC format.
Exactly.
And I think it's the servo library. Like I mean, the name of the library is actually literally just servo.
Yeah. It's one of the first examples, I think, like that I went through with an Arduino. So yeah, there's a lot of tutorials.
Yeah. That's one of the things that is really wonderful about this whole open source ecosystem, is that so many people have done the hard work of writing these libraries to do all of this fancy stuff, so that we don't have to. There's an example, there's documentation, the library's already written, you just include it, call it, and bam, it just works. And that's what I love about the whole like Arduino open source ecosystem, is just being able to stand on the shoulders of giants, and be able to get so much done with so little work.
Yeah, I like the open source component. And then when things don't work, you have a lot of online resources to search that have probably already encountered and solved your issue. And then in some cases, if you can't find that solution, or you want to do something close but a little different, I've actually gone into the source code of the drivers that are interfacing with the particular sensor, and made some changes myself there too. So, and at first I would have never thought I would even know how that works or what it does. But the Arduino platform kind of gives you a good foundation to, like, okay, I know this is how it works, and I want to change it. And you can go in and kind of expand your knowledge to tweak what you want to get things working.
I had a question about, I thought it was a pretty good reference, and I put it in the chat. It's called Pi Image Search. Is a lot of people in the group, are they familiar with that? No?
Ray, it's really hard to hear you, but I think you were asking about Pi Image Search, and is that for the Raspberry Pi?
Yeah, it's primarily Raspberry Pi. It's OpenCV routines. The guy that owns the site, sells a lot of the material, and that's how he supports himself. But I thought it was an excellent reference for anything OpenCV related. He does have a few things either for the Jetson Nano or for the Google Corral. But if you're interested in, computer vision, that for me was a site that helped an awful lot. You can download his examples and, try things out, and, just get more familiar with how OpenCV works, how machine learning works, stuff like that. So I highly recommend taking a look at it if you're interested in that kind of stuff.
Oh, is it piimagesearch.com?
Yes.
So that guy.
Yes.
Cool. Oh, Pi as in, that's Pi as in Python, not Pi as in Raspberry Pi.
That's true, but a lot of the stuff that he did, was for the Raspberry Pi.
Oh, okay. So it's Pi image search.
I guess, yeah.
Oh yeah, I see down at the bottom there's a bunch of stuff that's related to Raspberry Pi on there. That's really
Yep.
cool. Actually, I've used OpenCV a few times in the past, and I have never. I haven't had too many problems. I understand a lot of people do run into problems with OpenCV, but I didn't. I've never had any problems with them, and I found that they were well, you know what it is? I was working with OpenCV JS, which is a transliteration of the C code from OpenCV into JavaScript. So it's an automated system that translates it over into JavaScript. And actually had a lot of fun with it, did a lot of cool stuff, and really enjoyed it. And was able to work. There was a gentleman, I can't remember if I think he's from Japan, who was doing some of the maintenance on that and was very responsive and answered questions and stuff. I understand that may be different from people's experiences with the OpenCV core group, but the OpenCV JS I would heartily recommend.
It's fascinating on the Jetson Nano usage there. I have two Jetson TK1 developer kits from way back. I tried to fire one of them up the other day, and it seems like they don't really support it properly anymore. So I'm probably going to have to look at getting one of the Jetson Nano boards to continue playing with it.
I've kind of experienced that because they move with technology. They're trying to sell with the newest and the greatest and the latest and so on. And I can feel your pain. I got a whole closet full of boards I don't use anymore, unfortunately.
Yeah, it is a little bit sad. I mean, I don't think the difference between the Nano and the current version is that much, but they have changed base architectures on the whatever you call it, the Tegra processors, and they suggest that you can load the old code. But when I tried loading the old code several times, it just one thing or another just didn't quite work. So, but I'm seeing you can get the Nano 4 GB development kit for about $210 Canadian here, so that's not too bad.
I think I've only scratched the surface on what the Jetson Nano can do. Of course, again, my focus is pretty much robots, and I like that. Okay, there's nothing wrong with that, but it is used in all sorts of different things now, and it just screams.
Well, I also got one of the Google cardboard vision kits, and it has a little processor that'll do facial recognition and various and sundry bits and pieces too. And I keep thinking I need to get to playing with that a little bit too, because I've always thought the best goal would be to find something reasonably usable but cheap enough that you could put several of them in there. So you could maybe have one for each camera, one for the audio processing, one for making decisions about what the cameras have seen and stuff like that, and cascade them into a network. But I got to find the time, and I got to kick myself in the butt a little bit.
I'm afraid that sounds all too familiar.
Anyways, thank you very much. That was great.
Oh, it's really been fun.
Yeah, you were talking about Jim, the some of the difficulties in training with well, I guess for David's question, with varying lighting conditions, and some of the first things that we did, we went to a museum. It's called the Bro Museum in Dallas, Texas. And the lighting conditions were horrible. They had these huge floor to ceiling windows that, you know, were probably at least 20 feet tall. The sun was shining in on this floor that was like a polished composite material. And, you know, basically the cameras were looking directly into the sun, and we were looking for orange duct taped cans on in this particular competition. And to make matters worse, a young Oriental girl with a bright orange dress stood alongside of one of the borders of this. It's kind of like a soccer field, and my robot went right towards her because she was the biggest, brightest orange thing in the room. So it's lighting conditions are everything, it seems like.
We have we have a group down here that does the donkey cars. When I say down here, I mean down in San Diego. And one of my friends was involved in that. The story that he told, I just loved, which is they were laying down this road, simulated road surface in a pattern, and then, you know, training the cars to follow the road, right? And then, you know, you would have these kind of races where depending on how well trained your car was and how well made it was, it would follow the road faster or slower than the other cars. So they moved to a new location, or they went to a competition at another location. They lay down exactly the same floor and everything, and half of their cars, or my friend's car for sure, just went crazy. It would just like repeatedly make a left turn at a completely wrong place on the track that didn't seem to make any sense. And after a long time of troubleshooting this, what he figured out was that the camera on the car was seeing not only the road, but also the building around the road. And there was an electrical box at the exact location of the first left turn on the road, or it would come, that electrical box would come into view at the point where it was supposed to make that turn. And there happened to be a different cabinet of more or less the same color at this new location, which was not placed, you know, in concert with this left turn location on the track. And the car was seeing that and going, oh, it's time to turn left. So he spent quite a little bit of time actually building a shield to constrain the vision of the car to only be able to see the road surface and keep it from. So I mean, he just did that with a mechanical shield, just put like like blinders on a horse, almost, but around the camera so that it would only be trained on the actual road surface.
I think
we did it. And oh, go ahead.
I was just gonna say, I think that's one of the advantages of these training routines is you're not just training on color, you're training on shape as well. And actually, you know, that sounds wonderful, but I've heard stories about Google cars, excuse me, missing stop signs because they had tree limbs in front of them. And, you know, that destroyed the shape. Even though the color was right, they couldn't see the stop sign and blew through the intersection. And those are the kind of problems you can face. But I guess that's more training, right?
Yeah, it all boils down to the size of your data set.
One of the guys that participated in some of the donkey cart challenges actually laid a course out in his garage, and trained it with basically tape on the floor to designate a lane, and then pulled the tape up, and the thing did just about as well. So that that kind of gives you an idea about how well or what cues it was picking up in whatever it saw in the field of view of the camera. And yeah, so it's like it didn't need that that tape on the floor at all. It did fine. So.
we've got a ways to go, guys.
Yep.
I think somebody told me, or I read somewhere, I can't remember, but like a third of our head, you know, is vision processing. I mean, we all have a pretty good vision processor and inside us, right? And 33% of our head is doing vision. That's how hard it is, right? So something to think about.
I've actually been I've been listening to an MIT OpenCourseWare series. Really cool professor who's I really like her. She's really animated and interested in it. But it's all about I guess cognitive neuroscience. Basically, you know, trying to understand what the different areas of the brain are and how they work and all that kind of stuff. And yeah, it's the whole back surface of the cortex, which I think is really kind of weird because the eyes are in the front, but somehow or other all those signals go all the way back down and then end up on the back surface of the brain. And it's huge. It's like the whole back of your brain. So if you ever get hit on the back of your head or something and you see stars, you know, that's exactly why you're seeing stars, because that's the image part of your brain that's getting knocked out. Yeah, it's a really complicated thing. And one of the things that she was talking about in the class, and that I think is really interesting too, is that the brain does a lot of pre-processing on that image data before it even gets back to that part. So it's doing a lot of processing to find things like, you know, if a particular pixel, let's call it, is on, you know, there's a neuron that will check to see whether or not the pixels to the left and the right are also on, or are there pixels above and below that are also on, you know, and at the same, you know, general level or the same color or whatever. And then there's like, there'll be another neuron that's just going like, is there a sequence of pixels going up, or is there a sequence of pixels going left to right? So there'll be one that just detects left to right, doesn't do anything else. And there'll be another one that just detects right to left. And that's, you know, like for almost every pixel in the brain. So just like, that just blows me away that all of this processing is happening before it even goes into that, you know, cortex area in the back of the brain. So, you know, when we're trying to train neural networks to just work directly with pixels, it's not a fair comparison, right? It's like trying to teach a one-armed robot to do the same job that a two-armed worker would do, right? It's well, right off the bat, there's a problem here, right? So I think it would be really interesting to see more systems that are designed where they're like pre-processing some data to give the neural network a little bit more to go on, if that makes sense. Anyway.
It makes sense, but I don't know how to do it.
Yeah. Well, you know, one of the things was this, the Connect, the Microsoft Connect, puts out that pattern of little infrared dots so that you get some structured light stuff going. And I've always been kind of curious, because I know that those are primarily used for 3D information. But I'm sort of curious what would happen if you just projected that and then used a camera that could sense it, that had the IR filter removed, and then just train on that data, because you would get a visual representation of both whatever the actual images that you're looking at with this kind of depth information overlaid on top of it, and maybe the neural net would train better, you know, because it would have that information somehow encoded in it. Anyway, just a random thought.
That's kind of what this university team that I'm working with is doing. They're using thermal imaging in conjunction with vision processing to do, you know, to add another, you know, to add another layer into it, kind of.
Are they working with like faces or things that would be a different temperature?
They are basically working with bodies as seen from above. So, you know.
Oh, okay. So yeah, they're going to be warmer, right?
Right, exactly. And that's how they kind of key on, you know, what's, you know, what is now. That wouldn't work too well for a dead person, obviously, but since we're hopefully looking for light people. You know, and then they have to then, okay, this is a warm thing, but it's a deer, so we ignore it, right? So that's why they're putting the thermal together with the vision.
Yeah, so it's fairly rare for dead people to be walking around. So I think that's
a lot of zombie movies out there.
This whole system is going to fail during the zombie apocalypse.
Hey, folks, just to jump in for a moment, I'm going to have to run off. But can I pass the host off to somebody and then just close the meeting down when everybody's gone? Anybody planning to stay around for a while?
Well, I actually have to head out here in another couple of minutes, so I guess I'll just say goodbye now. And you guys.
Yeah, me too. It's
okay.
Myself also.
Okay. Well, then I guess we'll just call it a wrap.
Thanks, guys.
Thanks so much.
Thanks. Sorry about that.
Thanks so much again, everyone. Really appreciate everyone's participation and contributions today. It was a great event.
Thanks,
For
everyone.
organizing it.
Great job, Donna. Thanks. Bye.
Thank you.
Yep, thanks.
Hi, y'all.
Y'all.